you can only decode if the equations you get are linearly independent.
But no, the connectivity will not make them linearly dependent because you have to go over a large enough field size. So I'm sorry, that intuition's off.
Okay, but that thing only depends if the field size is extremely large.
No, it doesn't have to be extremely large. I just gave you the bounds. No. I mean, I can see where it's going, but that actually doesn't hold.
I agree in the case when you are talking about only for the random network coding. My question is for the array reliability. You send a bunch of packets, receiver doesn't receive them. You again send a random linear combination of the packets and each node combines them.
Yeah.
Suppose each node is connected to each other node. So the network is forming a tree.
Yeah. No, no, it does help. No, that is not a problem. That's off. Sorry. We can talk about it later, but no, I don't want people to have that impression. Okay, that the high connectivity does not hurt; it actually helps. Okay. Okay, since all coding is linear, I can write any packet X as a linear combination. So remember, every packet X is some combination of the original messages or packets or chunks of packets. Right? So again, imagine this vector of chunks of a packet within a packet. And the vector gamma is the global encoding vector of the X, and I'm going to send the global encoding vector along with X. But again, I don't need to know exactly who did what to whom because it's just an end-to-end process. Even though I'm doing coding in the middle, the decoding only cares about the end-to-end process. It does not care about who did what to whom. Okay? And by the way, people have a lot of trouble with that. You know, a lot of people say, well, but wouldn't it really help to know that at that edge? I mean, it would help if you told me ahead of time. But after the fact, it doesn't help. You know, what's done is done. Okay?
So when
yes,
you're
Ali?
forwarding a packet, you're actually overwriting the overhead that's derived.
That's right. That's right. So what's going to happen, let me write it down here, maybe if it's a little clearer. I have a coded packet. I have a coded packet which is, alpha 1. Oh, I called it. I have a coded packet here which is some gamma 1, gamma 2, gamma 3. Let's say it's of 3. Okay? So this is the code for packet 1. And then packet 2 has gamma 1 prime, gamma 2 prime, gamma 3 prime. Okay? So basically what I'm saying is that packet 1, so X is equal to the sum of gamma I of the original WIs for I equal 1 to 3. And X prime has the same thing. All right? And now I'm going to take these two packets, and I'm going to do an output packet, let me call it X double prime, which is a linear combination, say, alpha X plus beta X prime. The coding vector associated with packet X double prime is going to be alpha gamma 1 plus beta gamma 1 prime, alpha gamma 2 plus beta gamma 2 prime, alpha gamma 3 plus beta gamma 3 prime. Now, if X prime had gone erased, my beta would be what? Would be 0. Right? But now I'm going to do this not just with, the ones that I got in, but everything that I got in the past. Okay? Yes, Adam.
A question about the K. So,
K is the, yeah. Mm-hmm.
So K is, we should think of K as relatively small. I mean,
No. K is the number of input messages, the number of inputs, so it could be huge. K is not the size of the field. K is the number of messages that come in. So I could have 1 million packets. K could be very large.
But my overhead, in describing these linear combinations is going to scale.
It's going to grow with k. So generally what people do is what, the folks at Microsoft call a generation, is that in order to keep the overhead at a, we can talk about it more later, but in order to keep an overhead at a decent level, they're going to only allow a certain window of k to be encoded together. Okay? Okay? But if it's truly rateless, then you're encoding over everything. And you decode when you got enough degrees of freedom to decode the whole thing. But you can chop it up. You can say, I'm only allowing this window of packets to be coded together. That make sense? Okay. There were 2 questions. Raise your hand again, because I don't know who had. Okay, yeah.
So my question is actually related. So the k makes it like more like a block code?
That's correct. That's correct. So there are different ways of looking at it. You can look at it in a completely rateless fashion, where you started out with having a limited number of k's. You can look at it in a block code fashion, and actually going back to the question that somebody had asked about delay, you can find error exponents over the entire network using these codes. Okay, so you can find end-to-end block code error exponents. I'm not going to go into it. Okay, but I realize that the majority have not seen error exponents, but basically error exponents are just something that relates the probability of error, the probability of not decoding properly, to the length of the code and to how far away you're operating from capacity. So error exponents are usually something that looks like this. Error exponents are something that looks like this. Probability of error less than or equal to, some fudge factor, some factor e to the minus n, where n is the length of the code, times something that goes roughly as c minus r, the capacity minus the rate that you're sending at. Right? So the further away you are from capacity, the better your probability of error is. The larger your length of the code, the better probability of error. Okay? So that's what an error exponent is. So here, of course, the C is going to be the min cut. The R is going to be the rate that you're transmitting. Okay? There was another question. Yes?
Yeah, my question was related to how long the receivers have to wait in order to encode the packet.
The receivers will have to wait until they get enough degrees of freedom. If the so there are 2 ways of looking at it. If you look at it over a block code, you can get error exponents, which is saying if you assume some sort of ergodicity in the system. By the way, the ergodicity assumptions are very light. You basically have to have ergodicity in the sense that you have to be able to define an average rate. Okay, so this is a very light requirement on ergodicity. So you can do a block code, kind of like what most traditional channel information theory would do. Block coding is saying, I'm going to take my block to be long enough that I'm averaging the channels, network in this case, right? I'm going to see the average network, which means I'm going to see the average flow with high probability. The other approach that you can take is say, that's not what I want to do. I'm taking a rateless approach, and then what I care is the mean time until completion. Okay, which may be short. So there were no erasures in my channel, fantastic. There were a lot of erasures, I'm going to have to wait longer. Okay, but we'll look at other, so that gives you a high level. Obviously, I can't go into those proofs. These are good questions. Okay. So the outline of the proofs are following. I'm going to keep track, not for the purposes of actually operating the network, for the purpose of the proof. I'm going to keep track of the propagation of innovative packets. An innovative packet is a packet whose auxiliary encoding vector, this, okay, the transformation to respect to the packets injected into a source's memory are linearly independent across particular cuts. So for the purposes of the proof, not for the purposes of operation, to not go forth and operate a network this way, but let me look at all the cuts in the network, and let me say, aha, I'm going to keep track of, wow, an echo. I'm going to keep track of the auxiliary encoding vectors. Oh, there's a gain there. Oh, I see. Thank you. I'm going to keep track of the auxiliary encoding vectors, and I'm going to say that new degrees of freedom have hit a cut when I get auxiliary encoding vectors which are independent. And this gets a little bit to your question why I was telling you no. Okay? So we can show that if the R0 is less than capacity, the input process is Poisson, then the propagation of the innovative packets through any node forms a stable MM1 queuing system. So again, you do not need Poisson processes to have this operate, right? It's just in order to prove that just.
Sorry.
No, it's okay. How many people have done Jackson networks? Jackson networks. 1, 2. Okay, never mind. You can make it look like Jackson networks. It was getting back to somebody's question had asked about, am I keeping track of the delay in terms of packets? Who asked the delay packet? Well, let me tell you a little bit about Jackson networks. It's a nice. Jackson networks are, they're nice. So Jackson networks is a classical queuing theory. By the way, if it's not obvious from this, I encourage you, take courses in algorithms, take courses in networking. Okay, and I guess we'll talk about it more on Wednesday. But if there's anything to come out of this, there is so much fun stuff to be done at the intersection. Okay, so absolutely try to take courses in those things. There's so many neat things that can be brought together. Okay, so let me tell you a little bit about Jackson networks. So Jackson networks is it's such a very interesting, very powerful result. So you know that obviously if you have a queue which has input processes which are memoryless, like Poisson, and then has memoryless service time, then the output is Poisson memoryless. But if I have feedback, the memorylessness dies, right? Feedback kills the memorylessness of the input. So if I have a network with nodes where they're interconnected and I can have loops, right? In general, the input process to a node is not going to be Poisson because of this feedback, right? But it turns out that the occupancy, if you have memoryless exogenous inputs, and by the way, you can also have closed Jackson networks. If you have a memoryless service time, the occupancy distribution at the queues is going to look as though it were MM1. MM1 means memoryless input, memoryless service time at each and every queue. And you're also going to get a product form, which means that the queues are going to look occupancy-wise as though they were independent. Okay? So even though the input processes are not memoryless, each node by itself is going to have an occupancy which looks as though the whole thing was memoryless. Those are Jackson networks. The same thing holds here, but instead of looking at specific packets, because original packets no longer have a meaning, if I just look at the occupancy in terms of innovative packets, new degrees of freedom, it's going to look like a Jackson network. Okay? So there's a very, very deep link here between something which started completely algebraic and something which is, classic out of the queuing theory literature. Okay, I mean, Jackson networks have been around since the 50s. Okay. So this gives you one answer about the delay issue there. Okay. So comments for erasure reliability, particularly suitable for overlay networks using UDP, wireless packet networks. The code construction is still completely decentralized, and of course, as I said, the scheme can be operated ratelessly. Okay. So I just want to give you a little bit of an idea. This is something out of a paper, Desmond Lunn. Let me show you the following. So what happens is, let me give you this is a simulation. Okay, so I have nodes here, and there's Rayleigh fading, and all I said is that I'm not looking at interference right now. Okay, we'll look at interference later. But basically, I have nodes, have Rayleigh fading from node to node, delay, distance dependent, the usual stuff you guys all know and love. And a packet is acquired by a node if the SNR ended up above a certain threshold, and below that I assume it's an erasure. Okay, so I'm not doing relaying, keeping track of partial knowledge, okay? Just you got it or you didn't get it. And here's a network size, number of nodes, randomly distributed. And I'm looking at different choices. The choice here, and what I'm looking here on the y-axis is average number of transmissions per packet, which means in order to get a successful packet reception from source to receiver, on average, how many packets does the network have to transmit? Obviously, it's going to grow with the size of the network, right? So this is end-to-end retransmission. This, if you will, is a proxy for TCP, except it's better than any sort of TCP out there, because what we've done is we have optimized it to minimize this metric. So you see what happens. The average number of transmissions per packet is going way up. The next one is end-to-end coding. This is, if you will, something like a digital fountain approach, as we talked about before, right? So I'm using an end-to-end erasure code, optimal code. Okay? This is link-by-link retransmission. What's link-by-link retransmission? Well, link-by-link retransmission means that instead of waiting for the last node to tell you whether you got it or not, every node in the middle tells you whether you got it or not. Okay? So of course it does better, because suppose that I'm transmitting to the back of the class and the packet is going along happily until the very last link. End-to-end retransmission, you would say I didn't get it, and I retransmit it. It goes all the way through the network, inducing a bunch of transmissions. Whereas link by link, only that last link would retransmit. Okay? By the way, these two schemes are fundamentally extremely different. But they tend to do the same here. And actually, there was a presentation by Towsley, Carouse, and some others at the last Milcom. They used a completely different setup, and they got pretty much the same result, which is interesting. So, I mean, there's such different schemes. I don't think there's something intrinsic. I'm sure you could come up with examples where they do differently. But I think there may be something there for random networks. Here, this is path coding. Now, what's path coding? Path coding is a look. This is something that people may have seen. There was a little bit of there was effort in this, particularly in the 80s. Nick Maximchuk and a lot of those guys were looking at, particularly in backbones, finding separate paths and then coding across the separate paths. You can see that this is a version of network coding. But it's a restrictive version of network coding. It's a restrictive version because I start out saying I need to have a bunch of separate paths. There's no reason why I should. Well, let them merge. Let them do whatever they want. Okay? And this is full coding. There's a huge gap. Okay? There's a huge gap. All right. So let me give you another. So again, we're going the pre-prandial more. Yes, Alex.
In the previous question, the previous slide, do they grow linearly in the number of nodes, or do we have any analytic result?
Which one? All of these?
I don't. Yeah, that's what I'm asking.
I'll give you some results on scaling later this afternoon if we have time. It's very hard to get results, as you know, right? General results, but I'll give you some later if you have a tree structure. It's mostly because it's so topology dependent. That's what makes it very hard. And sort of typical results from random graphs don't seem to get you very far here. That's a good question. Okay. Any more questions on this? Okay. Let me just give you a very good example also of why this random coding helps. So suppose that a sender is in a bad spot. So I have 0 probability of loss on these, links. This is good. So 0 is good. 50 is bad. Okay? This is my probability of loss. It's my epsilon. It's not my problem. It's not my throughput. Okay? So a traditional network, wireless network, would try 1, right? And the probability of getting there would be 50%. So spatial diversity to the rescue. This is not surprising. You would transmit it all the way around. But if I was doing a route or forward packet, my probability of loss would still be high. So what happens is if I do non-coded, suppose I send P1 to P10, I send P1 and P2 first. So these two middle nodes, let's call them routers, right, have P1 and P2 each, and then if they forward, there's no real benefit. Whereas if they forward random combinations, each of them can just send one combination instead of having sent each of them 2 combinations like I did right before, right? And I can save transmissions. So the randomness prevents duplicates, and we'll see that more later this afternoon when we look at downloading. So the network coding is exploiting here the spatial diversity to improve dead spots, right? Now, mind you, this guy could only have gotten in the first place just that one packet which was combined. There's no way he can decode. This is not a decode and forward. This guy may only have enough capacity to get half the packets, and that guy half the packets. It's not a decode and forward. Right? But what I'm doing is I'm preventing duplicates. Okay? And I'll just show you, and of course it benefits multicast as we just saw. And again, without coding here, I have the source. Let me see the time. I have the source, and I have those 3 destinations till 12:35 again. 30. Oh no, I didn't know. The last time was 5. So I just there's a granularity. 32.5. Okay. So network coding also benefits multicast in the sense that here, suppose I have these 4 packets. If I just sent them in the usual way, this guy would be missing 2 packets. This guy would be missing 2 packets. This guy would be missing 2 packets because they're not the same packets. I would have to retransmit packet 1, packet 2, packet 3, packet 4. In random coding, I just do a random combination, and 2 transmissions should get me everything to everybody. Okay? And let me just show you again some more. Again, this was designed to be pre-lunch, sort of light. This is an experiment at MIT. This is Dina Katavi's group, who was my collaborator, on a 20-node network. And here's a CDF of the source destination pairs. There's 180 in that network. This is actually implemented. Okay? So here's my throughput in packets per second. Right? High is good, low is bad. So current. So this is fairly good routing scheme. Okay, this is a non-stupid routing scheme. This is the red, and this is with network coding. So what happens here? If you assume that this is a dead spot, I'm getting so little that I'm not happy. The network coding is maybe not helping me much if I'm already one of those nodes that's doing well. I mean, heck, if you're doing well, what can I do for you? There's not much I can do for you. If you're doing badly, I can do a lot for you, right? So if you zoom in on that part, if you zoom in on the worst 10%, there's a 6-fold difference there, roughly. Okay? So when people say, how much capacity do I get through? Well, maybe, what we've seen, right? You can send fewer transmissions. Sometimes you will get an improvement in capacity, but not always. The biggest thing is when things are bad, you do so much better, right? Because you're having a lot of losses. You're in a challenged environment, okay? So your improvement when life is bad is huge by coding, which is the same thing as you have in other systems, right? I mean, if you have a fantastic SNR and you don't have that much to transmit, and even a wireless link, what? Don't bother coding. Or, use some wimpy little code. Just open Linux Castella, pick one at random and whatever, right? I mean, really, then what else do you need, right? I mean, things are good. You don't really need coding, or you can get away with just a little bit, right? It's when things are bad that this helps you. Okay? And let me just... So then I'm going to go then into optimizations. I'm wondering whether to have a little movie, which I was going to show later, but maybe I'll leave you with a little movie. How's that? Pardon? It's a general audience. Yes, don't worry. Okay. Let's see. Where is it? Oh, here we go. Just going to this reliability thing, though. Okay, so I don't know if sound. Can you hear it? Does the sound go there? Give me. I mean, not that it's okay. I'll show you cope later, but. Well, whatever. I mean, on one side it's good, on the other side it's bad, right? So there you go, one movie, and here's another movie. I don't know, we'll go into cope later, but... So you see, thanks to network coding, grad students can waste more time watching movies over bad channels. This is a great improvement. And I'll show you cope later. Yes, yes, in Chinese and English. The network coding works for both. So that's a happy thought. Okay. Before we go, are there any more questions? We have a couple minutes before lunch. Are there any more questions on anything we did today? All right. I'll see you this afternoon. Okay, welcome back. So our dessert for lunch is going to be optimization. And we're going to do, I mean, up until now, we've really either done, worked around in the algebra, tried to get results. Then a little later in the day, we try to see a bit how these results linked to actual algorithms and actual ways of running the networks using network coding. And one of the things that we're going to try to bring today, this afternoon, is this whole aspect of optimization. And actually, before I go to that, let's go back. No, actually, let's go back to, again, this original butterfly figure. And ask ourselves, in general, how would we optimize? So there are going to be a couple of things, right? Sometimes it may be that you end up with a network like this, with a bottleneck, and you say, aha, it is only through network coding that I can get stuff through. But very often, actually, it may still be doable. It's not that you don't have physically enough capacity. It's just that it's going to be expensive to do it, right? So you don't want to only look at cases where it's doable with network coding and not doable with that network coding. You like to see how network coding helps you in a broader sense. And in particular, one of the things that you like to see is how do I set up my network code to be able to get a cheap operation of my network. Now, when you look at this, you say, oh my goodness, it's going to be a nightmare, right? I mean, let's face it, trees, just plain old trees for multicast are a nightmare, right? The Steiner tree problem is NP complete. It's not only NP complete, but it's even hard to approximate, right? And, coding in itself is tough. I can see where this woman's going. She's going to make trees and combine them with coding. We'll be here until the end of the week, right? So, fortunately, the answer is no. Okay. The answer is no, and we're actually going to be able to use a real separation between network coding and the subgraph over which network code. And remember that what we've shown this morning is that in multicast, as long as the min-cut max flow holds from the set of sources to each and every receiver individually, then there exists a code, which in general can be chosen randomly in a distributed manner with high probability of success, which will achieve the right throughput. Right? So now, the question is going to be really, how do I select those subgraphs? How do I select the subgraphs? So this whole portion on optimization is actually going to have here for a long time, just no codes with it whatsoever. Okay? So, let's look, and we're also going to look at distributed approaches. So let me look at what happened. Let me look at the same example as I had before, except I've taken the butterfly, and it's a dead butterfly. It's lying on its side. It's very sad. Anyway, so what you can see that happen here is, in effect, is I had two trees. I had a red tree for bit 1. I had a blue tree for bit 2. And what I did here is I was able to combine the blue and the red tree. Right? So what I did here is I was able to combine, and so you can imagine that what the trick was, I needed to have enough overlap between the two trees for me to be able to combine them. But I couldn't have, say, the blue tree and the red tree just completely overlapped on top of each other. Then I wouldn't have enough degrees of freedom arriving at the receiver. Right? So you can imagine building trees and making sure that they overlap enough that you get some sort of synergies, but not so much that you don't get enough degrees of freedom, right? I mean, so you can imagine, but what a pain. Okay. Instead, what we're going to do is we're going to take a completely different approach, and an approach which is very similar to traditional Bellman-Ford optimization in networks. And one of the nice things about this approach is, in particular, that it can be implemented in a distributed manner, where all the nodes are simply going to be able to communicate with each other, giving each other prices, costs, and using that distributed information that's shared just among neighbors, we can find a global optimum. Okay. So just to give you an idea, because I'm not going to be able to, of course, teach Bellman-Ford. How many people have seen Bellman-Ford? Okay, so the majority of you. Okay. All right. So here's the optimization. So remember that one of the things in this multicast network coding, we've been much more receiver-centric. Remember, in the end, the receiver says, for instance, I don't care what happens in the network. I'm just going to look at the packets and their associated encoding, auxiliary encoding vectors, and I'm just going to pick up as many degrees of freedom, and I'm going to invert, when I can, right? It's really sort of a receiver-centric thing. As long as the receiver gets enough from the set of transmitters that he's interested in, we're done. So it's going to be the same thing. Rather than look at a traditional flow-based approach, where you keep track of flows, we're going to do everything in a very receiver-centric type of setup. So what we're going to do is we're going to minimize f of z, which is the function, some convex function of z, the physical flow in the network. Right? But the physical flow does not correspond one-to-one with the degrees of freedom. And let's see what this means. So let me look at each link here. What do I have? I have in black the Zij, which is the physical flow that's going through here. Bless you. Okay, so there's actual bits that I have to pay for. Okay. And then I'm looking at the benefit in terms of degrees of freedom, but it doesn't have to be an integer, right? Of course, I can divide, time and whatever. I can do the usual granularity tricks to get real flows out of actual integer transmissions, right? This is the benefit that accrues to receiver 1 from what's going along link ij. And this is the benefit that accrues to receiver 2. As you see, receiver 2 is purple, receiver 1 is green, right? And that way we see what accrues to each. So what happens? Well, first of all, the number of degrees of freedom, again, could be in some average sense. Right? Remember, all we care about is the min cut. So, algebra is, it's gone at this point, right? We won't revisit it for a little while. There's no algebra. Well, there's real algebra, but yeah. Okay, so all I care about is the degrees of freedom, but the degrees of freedom, the flow for a particular receiver cannot exceed the physical flow. That's to say, I cannot transmit 2 bits and expect those 2 bits to offer me more than 2 bits of information at the receiver, any receiver. Now, what they can do is, of course, provide 2 bits to more than one receiver. Right? So it's not a zero-sum game among the receivers. So the virtual flow, the benefit accruing to receiver T over link ij, first of all, cannot be negative, but also has to be no greater than the physical flow. And then, instead of having the usual conservation of flow equations that we would have for Bellman-Ford, we're going to have conservation of degrees of freedom in the following sense. The degrees of freedom entering a node for a particular destination compared to the degrees of freedom exiting the node and which are accruing to that particular destination is going to be R if the node is a source, because that's where stuff is coming in, minus R if the node is a sink, and 0 otherwise. Now, the inequality is clear, right? I cannot create degrees of freedom. But you could imagine that I could take more degrees of freedom than I need, and I could just throw them on the ground. Right? So it doesn't need to be equal to R. But on the other hand, I'm going to have a complementary slackness issue here, where why would I be sending degrees of freedom to throw them on the ground? So you might just as well put it equal rather than an inequality. Right? Because these degrees of freedom, if I'm sending them for no reason, they're eventually going to push up my z, which is then going to reflect in the cost. Okay? So what I'm doing here, the big thing is I'm indexing on receivers. So it's a receiver-centric view of degrees of freedom. Very much like the stuff that we've been talking about this morning. Receiver-centric degrees of freedom, that's it. Okay? Rather than keeping track of different processes, like in the picture that I had before, I had a red tree or blue tree, and I had to figure out how the two were interacting. I can do this not just on graphs, I can do this on hypergraphs. For instance, in a wireless system, I could have a hyperedge between I and JK, right? Which means, for instance, that if I transmit from I to J, K hears it for free. Right? So it does not need to be a simple graph. It can be a hypergraph, and of course I can have hyperedges with several inputs. I mean, whatever makes sense. So for any convex cost function, the vector z is part of a feasible solution for the optimization problem if and only if there exists a network code that sets up a multicast connection in graph G at an average rate arbitrarily close to R, which was the rate that I was shoving into my network, from source S to the terminals in the set T. And of course, that can expand this to several sources. Okay, and the proof flows from the min-cut max flow necessary and sufficient conditions immediately. Right? So you can see one direction. Of course, if I have enough degrees of freedom at the sink, I'm done. That's a min-cut max flow. Right? And conversely, right, if it's working, it must mean that the min-cut max flow is satisfied. So our min-cut max flow for multicast, which we had to use network coding for, gives us the fact that this is a sufficient program. And now look at this. It is ridiculously simple. Right? We have a convex function with a small number of linear constraints. Right? Anybody coming out of a first term graduate school optimization class can solve this. And some people do it even in undergrad. Right? I mean, this is now a complete gimme. Now, what is the relation between this and Steiner trees, by the way? Right? Because Steiner trees are hard. How come Steiner trees are so hard? Right? How come Steiner trees are so hard and this is so easy? How come that putting coding made the whole thing easy? Right? Well, what's happened here is we've removed the integrality constraints that made the Steiner tree hard. That's what the coding allows you to do. Remember that I said this morning, what coding allows you to do is move away from switching matrices, from matrices that are basically permutation matrices, to general kinds of matrices. What I've done by doing that is removed an integrality constraint which was embedded in the fact that I was keeping permutation matrices. Okay, so this is a relaxation of integrality constraints on a directed Steiner tree packing problem. Okay, now most Steiner tree approximations are that tend to be on undirected trees, but there's some on undirected graphs, right? But that's what it is. So the proof. So it's polynomial time, okay, and obviously it's not something that we proved. It's just because, convex function linear constraints is polynomial time. And the nice thing also is it can be solved in a distributed way. The different nodes can now basically do what we said we would like to do here, which is just operate as honest middlemen negotiating with their direct business contacts. So let me give you an idea. I'm trying to network code broadcasting stuff to the back of the room. And all of you guys in between are going to just take stuff from somebody in the row in front of you or next to you and give it to somebody that you can, extend your hand to. And as we go along, there's a cost in the transaction, right? And I want to find the best price to getting to the back of the room. Now, I could have a bird's eye view, and I could say, oh, I can see the subgraph. I could make the subgraph. But instead, what I'm going to say is, I'm just going to ask the people I have contacts with here. I said, hey, how much does it cost to get to the back of the room? And you say, well, I'll charge you $1. And then I'll ask my friends, okay? And then, so he's going to charge me $1 plus whatever, his friends that he can have direct contacts with tell him. And they're going to look around. They're going to look up for the best deal, right? So if in the end your deal's not good, well, I'll go to you. Right? So, for instance, when we go buy soap at the store, we want, the cheapest deal on soap. I don't go, oh my goodness, let me look at the whole supply chain of my soap manufacturer and let me optimize that, and then buy my soap. I mean, I don't want to do that. The problem is, the supply chain's problem is the supply chain's problem. In the end, I'm just going to look at the price of the soap, right? And if one of the people in the supply chain of soap 1 starts becoming too expensive, then either soap 1 will become too expensive and I'll go to soap 2, or soap 1 will get, soap 1 manufacturer will get its act together and find a different supply chain. Okay? It's exactly the same thing. We're all honest middlemen. Obviously, if you start lying about the price, then it becomes weird. But then you're going to have to pay for it. So I guess it's your problem, not mine. But I'm just going to find the cheapest way to get to the back of the room without having to know how I got there. Right? You just need to talk to your friends and figure out your own supply. Okay? By the way, this idea of lying is not, you would say, well, why would anybody lie and say you're cheaper than you actually are? This is actually denial of service, by the way. That does happen in networks, right? I can be in BGP and say, I'm the shortest distance to the whole internet, and everything comes to me, and I brought the whole thing down just by lying. Okay, so if you say, well, why would anybody be so stupid? It actually is not a bad denial of service if that's what you're out for. So, how do these costs look? Well, a traditional cost would be something like in, just out of straight queuing, 1 over 1 minus rho. One over 1 minus rho, right? Where rho is usually the load, say on a queue, so rho is, lambda over mu. Lambda is the rate of arrival, mu is the rate of departure, or equivalently 1 over mu is the mean time for service, right? So if I have something like this, then what happens is as I'm approaching the capacity limit, which is rho equal 1, the thing just grows, right? So delay, queue size, this is the way things grow in queuing. So that's an example of what's one thing I can use, right? But generally it's going to be convex. It has to be convex, right? Otherwise I would be doing better by doing time sharing. Okay. All right, so let me give you a wildest example. So we ran this on rocket fuel, which is a very common, sorry, there's been a little bit of shift here. Obviously, this should all be shifted over 1. So rocket fuel is a very common optimization, practical ISP emulation, so that you can, if you want to try to see if your system works better than another system, you will generally run it on rocket fuel. It's kind of an accepted common play area for protocols. Okay, and what we did here is that we have a directed Steiner tree approximation, and here we have network coding. Okay, generally most existing multicast systems will do far worse than directed Steiner tree. Right, directed Steiner tree is hard and has to be done centrally. Okay, so this is just by the way, the costs here tend to be congestion costs. So think of it roughly as delay congestion, right? But without taking into account the decoding delay. So you get benefit. It's not necessarily the most dramatic benefit, but you do get a benefit. Sometimes it's larger relatively. Sometimes it's relatively maybe not as big, but you always do better, right? And the point is also it's easier. I mean, the optimization that you're doing is much easier. So if you say, well, should I go through the extra effort? At least in terms of the optimization, you didn't go through extra effort. You went through far less effort than doing the directed Steiner tree. So let me talk briefly about the distributed approach. And of course, this is a little bit beyond the scope of the class because, it's really how do you do distributed Bellman-Ford. But as you know, so Bellman-Ford, in most current routing settings will tend to be done centrally because it was generally done at a subnetwork level and you have a pretty good knowledge of what all the nodes are doing, so you'll tend to run it centrally. But one of its beauties is that it can be done in a decentralized fashion, which means that, just as I said before, if one of the intermediate nodes, one of the middlemen, goes away, or the link to that middleman changes cost dramatically, you can completely change the whole thing in a distributed manner, right? The network will eventually find its way around that. So what you do is you have to go to the dual, right? So the original problem was to minimize f of z under a set of constraints. Here you're trying to maximize, right? So if you haven't seen this thing before, think of it this way. It's the same thing for me to say, I want a bar of soap. What's the least amount I can pay for it? As for me to say, I have $2. How much soap are you going to give me? Okay, so imagine soap is, continuous, not discrete, right? But so suppose you see those places you can cut your own soap. So anyway, that's where it is. You can cut your own soap, and this is the same question, right? So it's one thing for me to say maximize the amount of soap you give me, as it is for me to say minimize the amount of money I'm having to pay you for a certain amount of soap. But what we need to have is that the costs work out. Okay, so these AIJs were the costs on the different links for a linear system. Okay, so it has to be that when I look at all the different pardon? Oh, sorry. I thought I said why. I was like, why? I was like, I didn't make this up. Yeah. I don't know what that f of t. I forget this f of t. I don't know what it's doing here. Just here. Yeah. It should really be the f of t is Well, anyway, I'll tell you in a minute. Well, the x of t is an f of t, so somehow something went awry. But anyway, so ignore this f of t. It just introduced itself surreptitiously while I wasn't watching. So basically, what I need to make sure is that the cost correspond to the amount that I'm paying, right? And then you also, of course, need to have no negative costs, because otherwise, things would get very funny. And at each point, what I'm doing is I am looking at this Q, which is maximizing the amount of soap. I'm looking at maximizing the amount of soap, which has to be within this bounded polyhedron of flow conservation constraints, where the flow conservations are, again, not on the physical flow X, not on physical flow Z, but on the X flow. Okay? So basically, what do you do to do distributed? Like in any optimization, take the dual. And this just happens to be the dual. You could do it other ways, right? And then what happens? You do the dual. So you consider a subgradient approach. You start with an iterate in the feasible set. And you keep solving a subproblem for each t. You obtain a new updated price, use projection arguments, and you keep going. And you keep going until you relate the new price to the old, until you converge, and then you use duality to recover the coded flows from the price. Okay? So just like if before I told you, this is how much soap you can get for this amount of money, now I'm going to tell you how much it cost me to get the piece of soap. Okay? Same thing as before. Now, this looks horrible, but it's not. Again, so if you have an optimization background, this is very benign. And I've shown you one way of doing it, but there are a lot of ways of doing it. There's a little bit of a trick, though. Convergence in the dual does not, in general, imply convergence in the primal, the original one. Right? So if my function's a little screwy, it could be that I got very close in the dual, but I didn't get close in the primal. That's to say that I got very close, and I can tell you that if you give me $3, I can give you a pound of soap, right? But if my piece of soap was 1.999 pounds, it's not $3 minus epsilon, because maybe my cost of the soap was highly bizarre. Okay, and I end up with, no, actually, it's $1,000. Well, it wouldn't be $1,000. Maybe it's 50 cents. It's just, there was a huge cost going from 1.999 pounds of soap to 2 pounds of soap for whatever reason. Okay, so these things can happen, right? You can often bound them, and there are ways of bounding these things. Actually, network coding has a very nice structure. The linear network coding the linear optimization that I showed you, that actually have a very nice structure, so that you can show that there is maintenance of feasibility in both the dual and the primal, which is not necessarily the case. But there are other ways of doing it. You can go all the time in the dual. You can go back and forth between the dual and the primal. You can do it asynchronously. You can do it in continuous time, right? So it's not like, everybody's on a clock and a node can only change its cost at a particular time in a clock. In a network, it may be quite asynchronous, right? So one node may decide that, so maybe you were giving it, maybe you were network coding by transmitting to the guy right behind you. The guy behind you leaves the room. Okay, we'll figure something out, right? He doesn't have to leave the room only at a particular set of possible times, right? So it can be asynchronous, it can be continuous time. There is a question, which is how many messages need to be exchanged for costs to converge, and we do have convergence results, which I'm not going to show, but let me just show you some experimental results, because actually what happens with these convergence results, there are very few convergence results for dual, by the way. Right, the sort of the Nedic-Bertsekis results, and then a handful of things. There's very, very little out there. So while I said at the beginning, from a optimization perspective, the things I was suggesting were sort of very simple. When it gets to convergence, they're not. Okay, that's not sort of bread and butter, simple optimization. Convergence is more difficult, but let me show you some experimental results. This is the number of iterations. So what we've done here is we compared the average cost in a wireless, 30-node wireless network, so using a hypergraph, with 4-terminal multicast. This is the network coding optimum. And up there is something called MIP, which is an algorithm by Visseltier and Efremides, which is a nice heuristic for uncoded multicast in wireless. Because it's empty complete, of course, but it's a nice heuristic. Okay? And here is the cost with a couple of different ways. So I showed you. I waved my hands and sort of vaguely pointed at one way of doing this primal dual. But here's some other, a couple other ways, and you see how it goes down, right? You see how it goes down. It actually approaches this, and this number of iterations is basically number of updates in not the information that the nodes give to each other, but number of updates in the algorithm that I showed you before, where you start with a P0, project, have a P1, project, get a P2. Okay, so it's number of local iterations. Okay, so it goes down pretty quickly, and then of course, as I said, it does react to differences. So again, here what we did is we had massive, rapid changes in the network. So for instance, a node goes out or the cost of a link becomes very different. And what you see down here is the network coding. What you see up there is that, of course, costs that may be small, changes that may lead to small costs in network coding may actually lead to large costs in non-network coding. Right? So this is, if you will, centralized non-network coding optimal, centralized network coding optimal. And here's a different set of different approaches, and you see that sometimes you get a ringing, sometimes you don't. Sometimes one rings and the other one doesn't, in terms of these algorithms. So if you're an optimization buff, there's just a huge amount of stuff to be done here. Okay, just absolutely. Did you have? Yes, Ellie.
What are you changing in this setup? Is it the cost function?
So yeah, no. What we're changing is actually it's actually the cost function among some of the links.
Because of some of them.
That's right. So some of the links have a rapid cost. They just change from one time to the other. You've changed completely the link cost, and this is to see how long it takes before that information disseminates so that you get back to getting close to the optimum, right? But the thing that you can see here is that even so, this distributed one is still doing better than the centralized non-coding one by quite a bit, right? So even under changes, it does much better. This is, until when do I go?
3:30.
Until 3:30, okay. So this is this is just looking at energy as a cost. Again, here's the MIP, here's the centralized, and you can see you do better with the centralized, and this is decentralized under different times, after 25 iterations, 50, 75, 100. And again, now when the cost is not like we saw before in rocket fuel, just delay and congestion, but energy, you can actually see that the difference, the benefit can be much larger. Right? You can very often get about 50% or so benefit. Right. By the way, if you ran on these and saw how often you cannot fit at all the connection in because network coding allows you to do it and routing does not, it would be a small fraction of the times. You know, experimentally under 10%. So again, it's not that network, I mean, yes, sometimes network coding allows you to do things that you cannot without. The main thing is almost always it allows you to do it more cheaply. Okay? So I don't know if it's after lunch and there are no questions, or what I'm saying is trivial, or, you know, nobody wants to optimize, but okay. So anyway, so one of the questions, of course, is can I set up a simplified graph? Because, you know, at this point, one of the questions that you should have, and I'm sure you all have, is, yes, but what if the information that I'm getting from the network in terms of costs is lousy? Right? Particularly in a wireless environment, I don't know the channel measurement. I mean, I pretend I do, but I don't really, right? I mean, we all do. I mean, we all pretend, but none of us do, right? So, you know, on a good day, I maybe know whether, you know, when I transmit, the other guy hears me or not. Okay? So let's go with that. Okay? Forget the channel measurement, the energy, the whole thing. Let's just assume that I can tell whether you hear me or not. That is pretty good. Okay? So you can do things, you know, one of the things that we try to do here is codecast is very simple. Basically, you keep a field if the sender is a multicast receiver and has received a previous block packet. And every node considers a neighboring node to be downstream if the neighboring node transmits a packet with a larger distance value. So basically what I'm keeping track of is distance as it's traversed the network. You could have had a loop, if I, you know, obviously from an energy consumption perspective, loops are not a good thing. But I'm transmitting these packets, and, you know, I decide that you're downstream for me if, you know, the packet seems to have gone, you know, less, you know, more distance where you are than where I am. Right, from what over here that you say. Because again, we can overhear each other. So every node maintains a local variable distance indicating the hop distance from the multicast data source. Okay? And then it copies its value to the code packet in the node it transmits. So every time a node transmits a coded packet, the distance is recalculated as 1 plus the biggest distance value found in the headers of the packets which were combined. Okay? So it's a very, very simple approach. It doesn't necessarily give you a tree, but it just means that now all I'm saying is, you know what, it's gone a certain number of hops and you're downstream from me. And that's all I know. And either you hear me or you don't. End of story. Okay? So, you know, we went from this, you know, beautiful optimization, very simple to solve, but assuming that I knew everything, to just, you know, the most crass heuristic we could come up with. Okay? And crass is not always bad. So H node also maintains, okay, so this wasn't the best name out there, NUST, but, you know, what can you do? Indicating the number of upstream nodes as a local variable, and it records its value. Okay, so it says basically, here I am, of the packets that I've combined, the one that's gone the furthest is this one, or rather this is the longest trip a packet that I'm combining that I'm sending to you has, and this is how many I have coming into me. So it's a very, very coarse representation locally of the topology. I'm not even keeping track of who's talking to me. Does that make sense? Just keeping track of how far I am from the source, how many people talk to me. Very, very broad, okay? And this was compared to on-demand multicast routing protocol, which is a very nice standard routing, non-coded protocol. And this is the performance. So here basically, this is the delivery ratio. This is with UDP. So UDP, by the way, is just you send the traffic. You're not waiting for acknowledgments. Okay, you just send it out. This is with UDP, and this is I'm not going to tell you what DP is. It doesn't really matter. But Codecast 8 means this is The field, this is F8. Okay, so 2 to the n, where n is 3. Okay, it's not a big n. This is not a large code. All right, and basically what you see is that the delivery ratio is actually improved quite a bit. Quite a bit. The other question sometimes is, what's the normalized packet overhead? Now, why the overhead? So there was a question this morning about, well, don't you have an overhead by having to transmit the auxiliary coding vector? And the answer was yes. We talked about what the overhead was. But let's take that overhead into account, along with the fact that if the overhead were not there, we would have to have more retransmissions. Right? So because the code is this rinky-dinky little code, what we see here is that the normalized packet overhead is still much lower, or significantly lower with coding than without coding. Now the reason I'm bringing this up is because I want to emphasize the reliability, the robustness of these optimization results. Okay, I didn't even have slightly wrong information here. I had almost no information, right? Almost none. I didn't even have a good local connectivity information. Nothing. Okay, very, very little. And you can already do better. Okay. Now, I'm going to talk a little bit. Actually, let me ask you guys at this point. So I can go and talk a little bit about optimization for joint network coding, source coding. Or I could punt it and give ourselves a little time maybe to do security. How many people for network source coding? How many? Okay, so don't be shy. I don't get it. Okay. How many people for network source coding? No, if you only raise it like this, it doesn't count. So if either you raise it or you don't. All right, thank you. So these are integers, these are Boolean variables. Okay. How many people is to security? Okay, security wins, so, especially because they raised it higher. Yeah. Okay, so there we go. Oh, I told you I would do source coding and optimization. Oh, the things we missed. Okay. Oh, it breaks my heart. Okay. So let's go and now talk a little bit about network coding and non-multicast. So remember that we started out with algebra. We bonded over this algebra. And now, and then we sort of moved away. We went into a little bit more heuristics, and we went entirely into the optimization realm. Let's go back now for a little bit, and let's reconsider the algebraic setup for the non-multicast. Okay. So let's remember fondly this general case of a set of inputs, a set of outputs. And in effect, what I'm going to have is I'm going to have different submatrices in my transfer matrix end-to-end. And remember that when I had multicast, I just had sort of M1, M2, M3, right? But in general, I'm going to have the submatrix corresponding to, at receiver 1, the sources at transmitter 1, at receiver 2, the sources at transmitter 1, and so on and so forth, right? So of course, when I had only one transmitter, I only had M1, M2, M3 because it was all from single transmitter. Remember that 3, that yellow, blue, red example that we saw this morning? Right? But in general, there's always sort of at the receiver, I'm seeing what these different impulses are. And so each Mij corresponds to one particular connection from one source to one receiver, and for a particular set cal X of connections. Right? Just like we did this morning. So what happens if, again, I restrict myself to linear codes? Remember that what we had done this morning is we had basically played with XIs, where XIs including the pre-coding, the coding inside the network, and the post-processing. Then everything that we did this morning was really trying to make sure that a set of determinants was non-zero. Right? But now, not only do we need to make sure that a set of determinants is non-zero, I'm going to need to remove the contributions of certain sources to certain sinks. Because if I don't want them, it's not so much that I need to be able to recover them. I need to be able to set them as 0. Now, of course, by the way, if I was able to recover them, I can trivially set them to 0. Right? The problem is, are they getting mixed in with my other things, and I can't pull them out? So this morning, it was pretty much just a getting enough degrees of freedom game. Now it's getting enough degrees of freedom from the ones I want and being able to extract the ones I don't want. Right? So it's not just getting multinomials in xis to evaluate to non-zero. It's getting multinomials in xi to evaluate to 0. And that is going to be much, much harder. Right? Because it means that I need to hit those roots. So before, all I was saying is, oh, I don't have that many roots, I just need to make sure I don't hit them. Okay, let me go with a big enough field, I'm happy. Now it's like, oh, no. I need to hit those roots. I need to not hit them sometimes, and I need to hit them when I want to hit them, which is for the receivers that I didn't want. Right, and in general, I may not be able to always recover everything at a receiver, right? But I need to make sure that that which I do not recover doesn't mess me up. So the things that we saw today where we had certain receivers that wanted stuff that was completely separate from the other receivers. Remember how I told you if I went to more than 2 levels, it became a pain, and then we would see it? Here's the pain. Okay, here's the pain for more than 2 levels.
What do you mean by 2 levels?
So remember I had a 2-level multicast this morning where one receiver wanted everything and the other receiver only wanted a subset? Okay? And so now I'm saying, suppose that one receiver wants everything, another receiver wants another subset, and so on. It actually doesn't work, right? By only looking at non-zeros. And this is the reason. Okay? This is the reason.
So why does it work in the specific case of one subset?
Why does it work in the specific set of one subset? Because of the structure of the matrix. Do you want me to bring it back up? You basically have one matrix that has everything, and the other matrix, see, I don't have a bunch of zeros all over. Right. When it gets to the point where I have these sub-matrices here, some of them which have to be non-zero determinant, and the other ones which do have to be 0 entirely. Right. That's when I'm really running into problems. Right. But there I had, one that was sort of by itself, and then the other one. So they were sufficiently separated. Now they're not separated. Right. It's when you have, non-zero, 0, non-zero, 0, 0, when you have a checkerboard. That's what makes it hard. Right? So it's really the... Yes?
I'm a little bit confused. So if you can do, you can achieve a rate for multicast, certainly you can do the same thing for 2-level cast, right? Because
2-level cast.
You said one of them only want part of them.
And that's what I showed this morning, 2-level multicast.
So even if he receives all of them, he can still get the part of it he wants.
Yeah, but you see, as I just mentioned, if you can get everything, you can always set it to 0. Yeah. The question is when you don't have enough of a cut to receive everything. Right? So if everybody can get everything, well, it's multicast. Yeah. Right? You end up taking some of the stuff you didn't want and throwing it out the window. That's your problem as a receiver, not mine as a network. Right? The problem is when you get a certain set of stuff, some of which you want and some of which we don't want, and the stuff you don't want is mixed in with the stuff you want, and you don't have enough degrees of freedom to recover everything. Right? In the multicast, you never have this. There's nothing you don't want. Number 1 is gone. You only have number 2. So your only concern is just to make sure that your determinants don't evaluate to 0. And we saw you can be completely sloppy about it. You cannot be sloppy here. Okay? Remember, these are still, the m's are still multinomials in the xis. Right? Now they have to evaluate to 0. All right? So that's why it's hard. Okay? So basically the multicast and a few what I would say sort of derivatives of the multicast, such as the 2-level cast and, all separate, those worked out nicely because the structure of the matrix worked out nicely. But in general, I'm in trouble. Okay? So in general, I'm in trouble because I need to find solutions to a system of polynomial equations, right? Before I was trying to make sure it was just not something that I'd evaluated to 0. Now I have to evaluate it to something specific. So it's harder to find solutions than it is to find non-solutions, right? So before we were trying to find non-solutions to 0. There's always, non-solutions are easier than solutions, right? And so another way to phrase it is, in multicast, everybody wants everything. In the general case, I have to really, really go out of my way. And on top of that, linearity may not suffice. And this is, actually, it's not been published. I shouldn't put it as preprint. I didn't update the slide. But basically, I'm not suggesting you build your network this way, but the point is here, this is something actually people in matroidal theory look at this particular network. The trick in this network is one side has an even characteristic and the other side requires an odd characteristic, right? And you can't have an even and an odd characteristic at the same time. Okay, that's what this...
Even if you code over time?
Yeah, because you need an even characteristic on one side and an odd characteristic on the other. So it doesn't matter if you code over time. So you're right. So there are examples that show that you need to code over time, right? This does not work because one side has to have an even characteristic, the other one has to have an odd. You can't have it both ways. Right? And that's why it's constructed this way. And I forget which one's even and which one's odd, but it doesn't matter, right? I mean, so this is one of the things that people use to show that in matroids you cannot always solve them using linear groups. Okay, so it's hard to do it with linear, and even if we could do it with linear, we still couldn't do everything. Right? This is an open problem, right? So there's a lot of work right now of people looking into whether matroids suffice or not. It's not easy. Okay, so what do we do at this point? So there's sort of a couple of things. So to some extent, we did multicast in the morning, and it was so easy. I mean, okay, so it's a bit. It was a lot of work working up the algebra, but then once we worked it, the results just fell on our lap. Random, distributed. The optimization is easy. I mean, we got so spoiled. And now we look at non-multicast as this, big cold shower. It's like, now what do I do, right? So, I mean, there are a couple ways of doing it. You could say, well, I'm only going to do multicast because I'm happier there. Everything's optimal and easy. Or you can say, well, that's not the point, right? The point is, as long as by coding, even if I'm coding in a very simple fashion, I'm doing better than by routing, then I should code, right? So just because I can't get to the optimum, it's not that I just give up. I do what I can, and I see how much better it does than routing. And the idea here, kind of going beyond multicast, and the reason I put all this up here is sometimes people say, oh, couldn't instead I use MIMO, or couldn't instead I use UW, couldn't I use all these other things that people do in wireless instead of doing network coding? And the point is, you can use